Dear students, in this session, we'll learn about mechanism of electrophilic substitution reactions. In earlier session, we discussed electrophilic substitution reaction in that just a reaction. Now, in this session, we'll be studying about mechanism. As I said earlier, there will be a difference between mechanism and a reaction. Reaction is single step. So react with each other in presence of attacking reagent gives a product. But mechanism is stepwise explanation. Mechanism is stepwise explanation. So in stepwise explanation, how the intermediate will be forming, how the electrophile is generating, how the carbon uranium ion will be forming, uranium ion will form, and then how it will be stabilized by resonance. So that in detail we will be studying as a mechanism. So mechanism of electrophilic substitution reaction, that is in benzene, electrophilic substitution reaction of benzene. This follows three steps. Generation of electrophile is nothing but to form from the reactant to form A plus. Next, formation of carbocation intermediate, in this case a benzene, in that any one with attacking of this electrophile, so that forms an C6H5 plus cation. Next, removal of proton from the carbocation intermediate. In the intermediate, Fn attacks, that will be consisting of a hydrogen in the same group. One of the hydrogen will be removed. Then we'll be getting mono substituted compound on the benzene. So this mechanism means mechanism of electrophilic substitution reaction will be consisting the three important steps. Generation of electrophile, step 1. Step 2, formation of carbocation intermediate. Step 3, removal of proton from the carbocation intermediate. So need to remember three steps. Then what we studied the equation in earlier, we'll see one by one. First we'll see general electrophilic reactions. In the first one, general electrophilic substitution reaction. In the first one, generation of electrophile. So how electrophile is generated? So the attacking reagent may not be strong electrophile. What we consider the attacking reagent may not be strong electrophile. So first, an electrophile is generated. Electrophile is generated by the preliminary process, basic process. So E and N. N is a nucleophile. E is an electrophile. What we take? The reagent. In the reagent, in presence of catalyst. Catalyst what we are using are anhydrous aluminum chloride or ferric chloride, or etc. These are the Lewis acid. Lewis acid means the catalyst role is to make the strong electrophile, the generation of strong electrophile. What are the catalysts? Which type of a catalyst will be using here? Anhydrous aluminum chloride or iron chloride. These are the Lewis acids. What we're using a catalyst, these are Lewis acids. So here, what we are taking the reagent, means will be consisting electrophile part and nucleophile part. So nucleophile take an electron from the electrophile, then it forms, means E and Nu. This is a reagent. I'm saying now it is an electrophile deficient of an electron. And nucleophile takes electron from that, hence will be having negative charge. So now it is E plus and Nu minus. During chlorination, alkylation or acylation of benzene, anhydrous aluminum chloride being the Lewis acid or catalyst, which helps in the generation of electrophile. Role of catalyst. What is the role of catalyst? What is the role of catalyst in the electrophilic substitution reaction, which helps to forming or generating strong electrophiles like Cl plus R plus or CO, acylium ion, respectively by combining with attacking reagent. So the attacking reagent combines with the attacking reagent, they generate electrophile. This is reagent E and Nu. So it takes an electron, nucleophile will be having an electron density. Then remaining part is positive charge. It forms an electrophile E plus. Okay. So in the first part, generation of electrophile. Example, we'll see chlorination. In chlorination, chlorine, Cl2 can be written as Cl and Cl bar. In chlorine, in presence of anhydrous aluminum chloride, AlCl3. So this is also as an example for catalyst, means role of catalyst. This also can able to explain role of catalyst. If Cl2 and Cl2, chlorine and chlorine. In that chlorine, so iron or aluminum chloride, AlCl and Cl, and this is Cl, AlCl. So what happened? This will take electron. If it drags an electron, aluminum take an electron because only this acid, electron acceptor. So one chlorine will be removed from this, means what will happen? This equal will be having partial, means electronegativity difference between them is 0. If we take an electron from this, it forms an electron partial positive charge. If it forms a partial positive charge, and what the compound will be forming is Cl delta plus partial positive charge is nothing but Cl plus positive charge, as well as AlCl 4 times an extra electron, no, minus. This is complex ion. This is complex ion which forms, no, this is chloronium ion Cn plus AlCl4 minus is complex ion. Okay. So this is how electrophile is generated. In the case of methyl chloride, CH3Cl, so AlCl3 will be using, it will take Cl from this, which form CH3 plus methyl chloride. In the case of acyl, CH3COCl. In the case of acyl, CH3COCl, Cl combines with Al to form AlCl4 minus. What will be the left behind? CH3, C double bond O, CH3CO, this acylium ion. This is how electrophile will generate. If this is how electrophile will generate, then this electrophile, the first part is over. First step, generation of electrophile. This formed electrophile, this involved in the intermediate. So due to this, after the formation, here the carbocation, second step, intermediate will form. Then after that intermediate, then carbocation, means removal of, after this carbocation, next removal of proton that takes place. First step, I hope you are getting the first step, generation of electrophile. So En is a reagent. En is a reagent. Example ClCl. If one side electron shift when we use a catalyst like AlCl3 or FeCl3, it will drag an electron towards here. One electron is nothing but from this itself. Instead of considering any catalyst, we can write E and N. So towards this is a Lewis acid, drags an electron. So which forms this part, N part. This E is deficient of an electron. N part is an excess of an electron, negative charge, and E is positive charge. This is electrophile. This is how electrophile will generate. Okay. Next, after the generation of electrophile, next, specifically they are saying in the case of nitration, electrophile is nitronium ion. nitration, nitronium ion, NO2 plus, is produced by the transfer of proton from sulfuric acid and to sulfuric acid to the nitric acid. So generation of electrophile in HNO3 and H2SO4. I think in the earlier session, I said how it will be combining. H2SO4 can able to write HO3SO and H, hydrogen, H2, S4 of oxygen, H2SO4, sulfuric acid. So this can be written as HSO4 minus and H plus. This H plus positive charge hydrogen ion combines with this oxygen in HNO3 of HONO2 group. So HOH is H2O. What will be the left behind thing? NO2 plus. This is nitronium ion. Nitronium ion. This is how NO2 plus will be formed. Right? So protonated nitric acid, and from that nitronium ion will be forming with the formation of water, H2O. Okay, so I'll write all this nitration, sulfonation, and everything. I'll write all the mechanism. I'll write. Okay, we are in first step only, generation of electrophile. So generation of electrophile in when we use chlorine, anhydrous aluminum chloride or iron chloride, Cl plus will form. That is in a chlorination. When the bromine, Br2 will be using so aluminum bromide or iron bromide, then bromination. If the mixture of HNO3 and H2SO4, NO2 will be forming nitration. From the sulfuric acid, concentrated H2SO4 will be getting sulfur trioxide, HSO3 minus sulfonic acid, that is sulfonation. Next, acyl chloride, alkyl halide treat with the, so aluminum halide, AlCl3R, AlBr3, that is Friedel-Crafts alkylation. So when we use acyl chloride, RCOCl, in presence of anhydrous aluminum chloride, okay, RC double bond O will be forming, that is called as acetyl carbonium ion or acetyl carbonium RCO plus acetyl carbonium. This is Friedel-Crafts acylation. One is Friedel-Crafts alkylation or EXA. So acyl group, RC double bond O group is there, no, that is acylation, Friedel-Crafts acylation. What the intermediate, what the electrophile will be forming? RCO plus. They will be attacking this, the group will be attacked here, C plus, that is acetyl carbonium ion. Okay, these are the electrophile, these are the sources, these are the electrophile, these are the source, and these are the reactions: chlorination, bromination, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. So you need to know the mechanism. So in that mechanism, formation of carbocation, next step, formation of carbocation is nothing but uranium ion. Uranium ion is C6H5 plus. C6H5 plus. So how it forms C6H5 plus? Attack of electrophile. When electrophile in first step, electrophile is formed. This will be attacks the formation of sigma complex. Sigma complex, E electrophile needs to attacks and sigma complex or uranium ion. Uranium ion should forms in the charge uranium ion. So in which one of the carbon is in sp3 hybridized, where uranium ion will be forming, where uranium ion will be forming, then we'll be having the sp3 hybridized carbon, means carbon single bond, carbon single bond. Example, this is benzene C6H6. For this electrophile attacks to electrophile electron deficient group, where electron deficient group attacks on benzene ring, where there the electron rich group, where will be the electron rich group, means carbon double bond, there the electrophile will attack. So electrophile attacks on the double bond here or here or here. Then what happened? So this benzene ring on this benzene ring, a double bond and double bond. If electrophile attacks here, so E binds with this double bond becomes single bond, hydrogen and electrophile. If it is double bond, this carbon will be having one hydrogen, one with this carbon. So this will be deficient. This will be deficient, forms and positive charge here. And this carbon, now all the carbon, or the carbon single bond. So that is an sp3 hybridization. This carbon under sp3 hybridization. This is the formation of uranium ion. Uranium ion. This is what we call as sigma complex. This is what we call as sigma complex. Second step. Okay, so formation of carbocation or uranium ion. After the formation of carbocation, uranium ion gets stabilized by resonance. So if it forms like this, like positive charge, then sigma complex or uranium ion so loses its aromatic nature because conjugated pi system. Here there is no conjugated pi system. Alternate double bond will not be there where the electrophile attacks. No. Then what happened? The delocalization, that character will be stops. Then where it will be ends, there the conjugated system ends from here to here, from here to here. Why? Because this electron can shift here, this electron can shift here. This forms a positive charge. After that own pose, there is no pi electron. So tilt to that carbon, sp3 carbon. So it can able to migrate. Pi electron can able to migrate. Okay, so see this how it will be stabilized by resonance. This electrophile and hydrogen. So if electrophile attacks to this carbon and will be having the double bond, means this carbon will be having 3 bond, right? One electron will donate to this, means will be having the insufficient of electron carbon bond. Double bond is decreases, means 3 of carbon will be forming positive charge. To satisfy this valency, means this electron shift to here. If this electron shift to here in this position, I'll write numbering from 1 2 earlier for the compound. We'll be considering 1 2 or 1 here, 2 3 second and third carbon, 3 4 5 6. Okay, this is 1. Electron will be shifting from 4 5 to 4 3. If electron shift from 4 5 carbon to 4 3 carbon, then on the 5th carbon electron density decreases, so we'll be getting the positive charge. If on the 5th carbon the electron density decreases, then delocalization has to take place, means stabilized by resonance. Pi electron migrates from where the pi electron 1 6 pi electron migrates to 6 5, means it will be stabilized here. If it becomes double bond here, then what happened? On the first carbon electron density is low, we'll be getting positive charge plus. To stabilize this, no extra electron, no pi electron in second carbon now, because is under sp3 hybridization carbon bond. Here this delocalization or stabilizing of resonance will stop. Aromatic character means delocalization, not aromatic character, delocalization will be stopped in this carbon. Now this hydrogen will be having an electrophile. It can stabilize by resonance through this, but it will end to the carbon under sp3 hybridization. Okay, uranium ion will be with the formation of carbocation. This is itself. This is what are these diagram? This will be stabilized by resonance. This is resonance hybrid structure. So 1, 2, and 3. After 3, we'll be getting the same first itself, the same diagram. No, so that is the resonance hybrid structure, same as sigma complex ion or uranium ion. We are in second step. And after this, the uranium ion, next the removal of proton should take place. To restore the aromaticity or aromatic character, sigma complex releases proton. If it releases a proton from sp3 hybridized carbon, here this will be the electron, here carbon double bond. So double bond, this is double bond, here an electrophile, and this will be an hydrogen. Now, what we used an AlCl4 minus Lewis acid, the catalyst. This will take the hydrogen from this. So, removal of hydrogen. Removal of hydrogen. If removal of hydrogen means it forms AlCl3 and hydrogen combines with chlorine to form HCl. Hydrogen chlorine with a combined to form HCl. Then what will be if hydrogen is removed? Then it becomes E. So mono substituted electrophile on benzene. Now it can be stabilized because if you remove electron, it forms a double bond. Now it can be stabilized by resonance. It's nothing but stable now. So mono substituted derivative will be getting this E and will be getting this E substituted. Mono substituted compound will be getting an example of AlCl3 or HSO4 minus SO3 group attack. No, these are the example. So first step, what is the first step? Generation of electrophile. First step, generation of electrophile. Second step, formation of carbocation intermediate C6H5 plus means electrophile attacks on the benzene ring, forms carbocation intermediate. And after that, this hydrogen will be removed. If one hydrogen will be removed, this hydrogen will be having double bond with this. If you remove hydrogen, this will be forming double bond. Again, it will be stabilized by resonance. Are you getting? Or the hydrogen will be removed. H positive charge. It will be removed, and this hydrogen will be shifting here. This hydrogen will be shifted here. This will be removed because we'll be having electron diffusion. Here is an electron diffusion. If it removes H and Cl as HCl, Al and Cl3, AlCl3, and this hydrogen will shift here, forms a double bond, proton. Hydrogen is nothing but proton, H plus. Okay, so these are the three steps. Now we'll see one by one. So just three steps mechanism means all the three steps. First one, mechanism of nitration means nitration of benzene. So I'll write just in steps because earlier we know that equation, nitration equation. So nitration equation is what? C6H6 benzene. C6H6 benzene. Treat with so concentrated H2SO4 and HNO3, mixture of H2SO4 and HNO3. Okay, so which is C6H5NO2, right? So this nitration. This is nitration what we got. So final equation. So we'll see mechanism. I think we discussed already the equation. We'll see mechanism. First one is generation of electrophile, right? Nitronium ion. H2SO4 dissociates to form, okay? So H, just a minute. So H2SO4 dissociates to form H plus HSO4 minus. So written SO3, HSO3 and SOH. H will be separated to form H plus and HSO4 minus. This H for the nitric acid HNO3 can written as HO oxygen and nitrogen NO2 group. NO2 group, if you want to write in detail, you can write nitrogen with oxygen double bond, nitrogen with oxygen single bond. Will be having a negative charge. So the nitric acid, this is what is nitric acid. So in nitric acid, a nitrogen will be having the positive charge. So we'll be having the pair of electron. We'll be having the pair of electron. So this oxygen electron rich group and it oxygen H plus. H plus. So how it will be formed? H. Can notice no? H, O and H. This is N double bond O and here a single bond O. On the negative, if it forms in positive charge, NO, this will be pair of electron. NO plus will be having one pair of electron and positive charge. So if it forms in positive charge, and here this electron will comes here. It forms NO2 plus. So H2O plus O double bond N and double bond O forms a positive charge. So this is right side part. This is, so I'll change the color. This is the right side part. Will be forming ONO. Will be forming ONO. ONO is NO2 plus. ONO is NO2 plus. This is what we call as nitronium ion. This is what we call as nitronium ion. This nitronium ion is electrophile. Nitronium ion is called an electrophile. This is over. First process is over. Formation of electrophile. Next, electrophile should attacks. I'll erase this. Clearly see this. I'll erase. Now I'll write. Second one, the electrophile attacks the benzene ring to form intermediate carbocation. Second step. In second step, NO2 C6H6 benzene is C6H6, right? C6H6 benzene. So here on all the carbon will be having hydrogen. For identification, just for the identification, I'm writing only hydrogen. So NO2 is electrophile, NO2 plus. Where NO2 need to attack electrophile? Electrophile attacks on the double bonded compound. Means if it attacks here, if it attacks in double bonded electron rich group, so we can able to write like this, benzene and benzene. So if attacks no NO2, this is the double bonded compound. One hydrogen, one is an NO2 group. So if NO2 attacks here, this double bond become single bond. So carbon will be having the positive charge. If carbon will be having the positive charge for only one, so after that what will happen? Double bond, here double bond, and here will be the double bond. Here double bond, and here will be the double bond. So this, I'll change the color, the double bond, this double bond shift here. If this double bond shift here, we'll be getting positive charge, right? And here is a double bond, the positive charge. Then this double bond shift here, will be getting the positive charge. We'll be getting positive charge. So again, comes to here, sp3 hybridized, then the hybridization will stop. So I'll write all the three structure. So this first one structure, this is the first structure, attacks hydrogen, and here is an electrophile NO2 group. So if it forms a positive charge, so we'll be having double bond and double bond. If it donates an electron to this, an electron to this, so here electron density will be forming. So we'll be getting structure, reversible structure, I'll write. So this possible, no, this keep on changing. Now it is one double bond here, and here hydrogen and NO2. And what will be here? Here form positive charge, double bond as it is. Now this will shift here. If that will shift here, this bond pair of electrons shift here, here will be forming positive charge, right? So we'll be getting, what is this? This is NO2 plus. So on benzene, so if it shift here, will be forming positive charge, which where is shifted? Here one double bond, here one double bond. So after that, for the shifting of pi electrons to here, there is no pi electrons. There is no pi electrons. So NO2 plus here doesn't have a charge. What happens here? NO2 plus, there is no pi electron. This carbon is under sp3 hybridization. If this carbon under is an sp3 hybridization, there is no delocalization of pi bond. Delocalization of pi bond. There is no delocalization of pi bond, then it will be stopped. It will be stopped. So we can able to write this together, all the three structures together, we can able to write like this, will be forming positive charge. So we can write half circle and we'll be writing hydrogen here and NO2 here. So not this is NO2, okay? NO2 here, clear? So this is formation of uranium ion or carbocation. Next, intermediate of carbocation, lose proton. So lose proton. So donation of proton. So donation of proton, earlier we'll be having an HSO4 minus. HSO4 minus, take an electron, take an proton, will be forming. Take an H plus, not an electron, take an H plus, will be forming H2SO4. This uranium ion, this uranium ion will be having, no, this is hydrogen and NO2 group. So this will be stabilized by resonance, but it will be ends in the first carbon because that carbon is under sp3 hybridization. Now this NO2 group, this proton needs to, which is the proton here, electron deficient group. When you consider any one, either this side hydrogen or this side hydrogen or electron deficient positive charge, this hydrogen get eliminated, removed, as HSO4 minus H plus become H2SO4, then this double bond will shift here. Okay, so I'll write plus HSO4 minus. This hydrogen, no, this hydrogen takes here, will be forming H2SO4. H2SO4. Okay, so this is NO2. NO2 plus H2SO4. This is nitrobenzene. This is nitration. This is nitration. Formation of nitrobenzene C6H5NO2 is mechanism of nitration. Similarly, we can able to write mechanism for other process also.